Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. We are in the 12th week and this is our second lecture. And if you recall, in the last lecture we identified the different topics that we are going to cover in this week. So the second lecture is dedicated on column design but with biaxial bending. Now if you recall, we have already designed a column, say a rectangular column having axial loading, and initially first we designed with axial loading and minimum eccentricity, right? And then we considered axial force and moment along one direction. So rarely this we have a situation where we have a load which is acting at the CG of the column. In most of the cases we have Mx and My, both are acting. Now when we have the load P along with two biaxial bending moments acting on the column, then the design is little critical because we have to follow some complex steps to find out the exact stresses at the extreme fibers and accordingly design the structure. Now, when we have, say, a building, mostly the corner columns and some of the edge columns are experienced, they're exposed to actually Mx and My. Sometimes also we have irregular layout. For example, if you have a column like this, then also we have a situation where we have moments in two orthogonal directions. Now, before we move into the details of how to design the column with two different moments acting along two orthogonal axes, let us first quickly revisit the axial load only case. Now, for that, again, we consider, if you recall, uniform stress distribution, right? And the load passes through the centroid of the section. Of course, we consider minimum eccentricity, and we also studied earlier the guidelines for the minimum eccentricity. Now, the governing equation for this case, where Pu is the sectional capacity, is given by this expression, where on the right hand side, the first part is the contribution from the concrete, and the second part is the contribution of the steel. Now, if you recall, if we have different layers of steels, we need to consider the effect of each and every layer and finally sum them up to get the total effect for this cross section where we have only axial load acting on the column. Now, if we have a one step harder case where we have the axial load along with uniaxial bending, then one of the axes, say it is x-axis, we can have other axis also experiencing some moment, but let us consider only one axis. Then, of course, the stress distribution actually becomes, it is following a linear model. So, and because of the combined effect of this P and the moment about X, we need to find out the stresses at the extreme fibers. Now, in this case, neutral axis shifts, and then, of course, load is applied through centroid, but again, we should take care of the minimum eccentricity. Now, for this, we have governing equations of force and moment for that section. Again, we have contribution from each layer of steel, as you can see here, and then we have also the effect of concrete. Now, if you recall, we actually discussed in detail these constants C1, C2 and how to design it completely. Now, C1 is the coefficient for area of stress block based on the location of the neutral axis. For that again, Pi is the percentage of steel at the ith layer. So we can estimate that. And ASI is basically the area of the steel of the ith layer. Now, these are the stresses. FSI and FCI are the stresses in steel and concrete at the ith row of reinforcement, right? And C2D, if you recall, is the distance between the centroid stress block and highly compressed edge. YI is the distance of the ith row, and obviously it is positive towards the compressed edge, right? So that's how we design the case against axial loading and uniaxial bending. And we also actually discuss the PM interaction curve, right? So for a given section, the sectional capacity and moment capacity, we can actually develop this interaction curve. So the governing equations based on stress block parameters and strength compatibility show that the axial load and moment capacities depend on these three things: reinforcement percentage, that is PI we discussed, distribution of reinforcement over the cross section, and the yield stress of steel, right? Now, this design is actually very demanding because if you recall, we need to assume the location of the neutral axis, and accordingly we need to go for an iterative solution, right? So multiple trials are required actually for this solution. Now, where the difficulty comes, the first difficulty comes actually from the location of the neutral axis. We need to exactly identify the location, and that's where we need to do the iterations, and finally we need to converge to the actual location. Now, the different factors that affects are basically the load, change in load, change in steel, and change in eccentricity, right? So now, manual design using stress block plus strain compatibility is indeed time consuming, as you saw earlier. It is iterative because we need to start with some assumption, then we need to verify whether that assumption is satisfied or not, and accordingly we need to improve our design procedure. And sometimes it is very impractical because for a large scale structure, we'll see in this week we are going to model a full scale structure. There, if we need to repeat this exercise for each and every column in each and every floor, then that is a very demanding task. Now, how to simplify that? And for that, code provides, recall, we went through some of the PM interaction curves that will go in details. So that simplified design is actually based on PM interaction. Now, first we need to go through what is PM interaction. This curve is drawn for a column as the load changes from, this is important, pure axial load through varying combinations of axial loads and moments to a pure bending case. I will explain that, just keep that in mind. I will show it in a minute, what is the meaning. So these curves are useful for determining the strength of columns, right? For various proportions of loads and moments. So any combination of loading that falls inside the curve is generally satisfactory, whereas any combination, obviously the reciprocal of that is falling outside, is considered as failure. Now, SP16 I showed you earlier, which is a design aid to IS456, provides this PM interaction curve for different cross sections and different steel combinations. If you recall, we'll see some example in a minute, but these design charts are already available in SP16. Okay, so here you can see a schematic diagram of the PM interaction curve. Now, in this curve, on the y-axis we have the load and x-axis we have the moment. So, the PM interaction curve, where P, that is the axial load, is in the vertical axis, starts from this point A. We'll see that in a minute. So it is a plot between axial load and moment. So it starts with maximum axial load where we have no moment. That means it is here. So the moment is 0. And then it ends at this point where we have pure bending and no axial load. And the curve, as you can see, it is non-linear, having different region that we'll see in a minute. But the first thing, it starts from this point A, where pure axial load is there, and then ends with pure bending. Now, let us quickly go through these points marked on the schematic diagram. So, point A is the point for pure axial load, which represents a uniform axial compressions without any moment. Now, point B is where we have zero tension. The strain in the concrete at the least compressed edge is 0 and the concrete begins to crack. Recall, if you have a cross section like this, and if we have a point load acting at the middle, so compressive stress due to point load P is here. So this is sigma axial, and then so this is P is acting, and if you have a moment here, so compressive say positive, then for moment, so this is bending, and say this is positive, this is negative. So when we combine these two, we'll have the combined effect. So depending upon the values of these two stresses, it may start with 0 and purely positive, or it may end up with this type of situation where you have this region is under tension. So point B is the case where we have zero strain, right? That means it is here. Point C, it is a balance failure in compression edge of concrete. It reaches its ultimate strain and yielding of reinforcement develops in the tensile phase simultaneously. So that is a balance failure. Then point D, which is the representative of pure bending, represents the bending strength of the member when subjected to the moment alone with zero axial load. So it is here. Now the region AC, which is here, if I mark this particular region, it is compression controlled failure. The column with axial load and moment capacity falls in this. Initially fails due to crushing of concrete in the compression edge before yielding of tensile steel, because it is governed by compression. Now this part is tension controlled, and it exhibits a large deflection in the reinforcement at the tensile phase before failure. So as you can recall, it is a ductile failure, right? Remember, in case of beam design also we discussed about this ductile failure, and we always advocate for under reinforced design, right? Now when we have this biaxial bending, so let us consider the stress strain diagram, and the equilibrium method tells us the governing equations for axial load, moment about x and moment about y. As you can see, again in this case we have the contribution from the steel and concrete. So as you can see, we also identified that in the previous case. Out of that, this y bar here and x bar here, they represent the centroidal distance of the stress block from the highly compressed corner along y direction and along x direction, right? So we'll see that block diagram in a minute. here you can see. So if you have a cross section where we have axial force and we have moment about x and about y, obviously the neutral axis is marked here, which is at an angle theta with the vertical, right? And accordingly the strain diagram here and stress diagram here. So now based on these diagram, as you can see, depending upon the orientation, this block in different region in compression or tension, it varies because of the effect of two different moments acting along two orthogonal direction. Now the main difference is actually here, where the neutral axis in earlier case it was perpendicular to the eccentricity, right? So, but here in this case, it is because of the biaxial bending at an angle theta. Now, if you recall, we have the PM interaction curve is something like this. This is the schematic diagram. Now, we have to extend it for two different moments. So, if I have another one, it will be something like this, and then we have to complete this for, so say this is mx and this is my. We'll come to that in a minute. Now, for a given cross section and reinforcement, by varying the inclination of the neutral axis, a series of interaction diagrams can be drawn, right? So, here is the theta. For every theta, we can find out these interaction curves. And the expressions earlier we discussed during our discussion on column design, right? Now, the complete set of diagrams for all angles will result an interaction surface. This is what? So, it will like this and it will form a surface. Okay, so it will form a surface. Each point on this surface represents a particular set of axial load Pu and moment about two orthogonal axes, which together produces the failure of the section. Now, here is the surface, as you can see. So, we have three different cases, three different extremes. So, we have case A, where we have only moment about x-axis, right? As you can see here. Now, second case, case 2 or case B here, is where we have moment about y-axis. Now, when we have neutral axis at an angle theta, that is case 3 or case C here, so we get this interaction curve. Now, so for a given cross section and the given set of reinforcement, we can develop this series of interaction curves, and then those curves are available in SP16. We will see, we'll consider an example in a minute, and then we'll see how we can use that curve to design, right? Now, this process again is iterative. Now, we have this method proposed by Bressler, and where this characteristic equation is given. So, we have to satisfy this condition, and then we'll see how we can design the cross section. Out of that, we have this MUX and MUY, the maximum uniaxial moment capacity. Recall, these are the moments where we have zero loading. Then this alpha is related to PU by PUZ, and then the values for different ranges of PU by PUZ are given here, and accordingly the alpha varies. So you can see for PU by PUZ between 0.2 to 0.8, it varies linearly between 1 to 2, and if it is less than 0.2, alpha is 1, and if it is more than 0.8, alpha is 2. Now let us see with an example how we can design a cross section. So we have a column size given here, 300 by 500. Unsupported length is 3 meter. Axial load is 700 kilonewton, and the factored moment about X is 100 kilonewton meter, while the factored moment about Y is 50 kilonewton meter. We are going to use M25 concrete and Fe500 steel. So these are the parameters given: load, moment about X, moment about Y, and LU. That is the unsupported length. Now, step 1, first we have to check the minimum eccentricity. For that, if you recall, IS 456 clause 25.4. So about Y, it is LU divided by 500 plus capital D, not small d, divided by 30. So if you put the values, unsupported length is 3 meter. So along Y, we have a minimum eccentricity of 22.67 millimeter. Similarly, along X, we can find out the minimum eccentricity, which is, in this case, it is 16 millimeter. Right. And then moment due to minimum eccentricity, we have to find out. For that, we know PU times the maximum eccentricity, which is about Y. So it is 15.9 kilonewton meter, which is less than 150 kilonewton meter. Hence, moment due to minimum eccentricity doesn't govern, and we have to now consider the biaxial bending. Now, in the step 2, first determine the uniaxial capacity about XX. So for that, first trial assumption is that we start with a percentage reinforcement of 1.5%, and then assume 40 millimeter clear cover and 8 millimeter tie and 20 millimeter main bars, right? So effective cover is the clear cover plus the diameter of the tie plus half the diameter of the main bar, so it is 58. So effective cover by capital D, as you can see here, it is 0.12, and P by FCK for us it is M25 concrete, so it is 0.06. Now once we have these two, then let us consider SP16, and in that SP16 let us consider the chart number 49, which is here. So this is the chart we are going to refer. So here you see the Fy for the steel we use, so it is 500 Newton per millimeter square, and here we use D by D, it is 0.12. So we use the charts for the closest value of D by D, which is 0.15, and then from this chart we will see in a minute how we can find out the moment capacity. Before that, first we find out PU by FCK BD, because if you look at this, on y-axis we have PU by FCK BD, and from x-axis we will get MU by FCK BD squared. So PU by FCK BD is 0.19. Now on the y-axis we have 0.19, so it is here. Then we have to consider the curve for P by FCK, which is 0.06. So here you can see it is this curve that we refer to. So if we come here and then on the x-axis, value of mu by FCK BD square is 0.11. Now from this value we can find out the capacity about Xx, which is 0.11 times FCK BD square, and that is 206.25 kilonewton meter. Now step 3, we determine the uniaxial capacity about y axis. Same procedure, repeat the same exercise. So d prime by d we first find out, then P by FCK, which is 0.06. Now we use chart number 50 of the same codal provisions. So we have Pu by FCK BD square, again it is 0.19, and from this chart number 50, the same way we did for the previous case, we can find out the value of mu by FCK BD square, which is 0.1. So the moment capacity about y-axis is 112.5 kilonewton meter. So we have obtained moment capacity about two orthogonal directions. Then we have to determine the axial capacity. For that we use chart number 63 of SP16. We have percentage steel 1.5%, Fy 500, FCK 25. And from this chart, as you can see here, on the x-axis what you have is reinforcement percentage, as you can see, and then we have PUZ divided by AG. So from this curve, we find out this ratio and then find out PUZ, which is 2475 kilonewton. Then finally, we check the capacity of the section. So we have Pu by Puz is 0.28, Mx by Mux is 100 by 206.25, which is 0.48. Similarly, in the y direction also we find out, which is 0.44. Now, recall from this ratio, we need to find out the value of alpha. So this is 0.28. Recall it is more than 0.2, less than 0.8. So we have to interpolate, and through interpolation we get the alpha is 1.3. Finally, we check this criteria which was shown you earlier here. We know now everything, the capacity along x and along y, and we know the applied moments along x, along y. We have already obtained alpha. So that let us see, it is 0.48 to the power 1.13 plus 0.44 to the power 1.13, which is 0.83, and it is less than 1, hence the design is safe. So you can see, if we use interaction curve, how simpler it is to design the cross section. Now we have to check for the capacity of the assumed section in step 5. For that, again, let us use SP16, chart number 64. So we have Mx by Mux as 0.48 and Pu by Puz as 0.28. So from this curve, we can actually find out Mu by Muy, which is 0.58, and hence it is safe. So you can see the values of PU by PUZ is marked here, and accordingly these curves are produced. So we can cross verify the capacity of the assumed section starting from X direction and going to Y. Okay. Now we have to also design the transverse reinforcement as per clause 26.5.3.2c, and then diameter of the transverse reinforcement should be more than the maximum of these conditions, 1/4 of the main bar diameter, which is dB, and 6 millimeter. So main bar diameter we have 25, 20 by 4, which is 5 millimeter or 6 millimeter. So it should be more than 6 millimeter. And then pitch is minimum of column width. In our case, we have column width, it is 300 by 500. Then minimum of column width 16 dB, dB is 20, and then 300 millimeter. So ultimately we get 300 millimeter, right? So we provide 8.5 diameter bars, tie bars at the rate of 300 millimeter center to center. That completes the design. Now let us try a different cross section for this same biaxial bending. Now in this case we have a circular cross section, right? Now when we have a circular cross section, because of the symmetry, we expect the capacity along X and Y to be same, and then we have to design that cross section against a factored load, axial load of 1000 kilonewton, Mx 125 kilonewton, and Y 80 kilonewton. Unsupported length again 3 meter, column diameter is given 500 millimeter, and again we will design it with M25 concrete and Fe 500 steel. In this case we will design with spiral reinforcement, right? That is an extra addition. So these are the parameters against which we have to design. So now what we do, we determine the equivalent uniaxial moment, because as I told you that it is a circular cross section. So we can actually design, so this is X, Y, we have Mx and My. So we can find out equivalent moment, and which is 148.4 kilonewton meter, and then we design it based on that uniaxial case where we have this resultant moment is acting. Again we have to check for minimum eccentricity. Along Y direction it is 22.67 and X direction it is 16. So moment due to minimum eccentricity is 1000 times the eccentricity, which is 22.67, and then again it is less than the applied moment, right? So you see along X we have, this is the moment, along Y it is 80. So it is less than this moment, and hence moment due to minimum eccentricity doesn't govern. Now again we consider 40 millimeter clear cover and 8.5 diameter bars and then 25 main bars. So we can find out D prime, that is 58, and D prime by capital D, which is 500, so it is 0.1. Now as per clause 39.4 of IS 456, the strength of a column with spiral can be taken to be 1.05 times the strength of a column with lateral ties, right? So the axial load and moments are decreased by this factor. So we have Pu by FCK D square, which is 0.15, and Mu by FCK D cube, which is 0.045. Now again we use the chart number 61. We'll see that in a minute, and here it is, chart number 61 for circular cross section. You just note the My value and the D prime by D value. Okay. So What we get is P by FCK is 0.04 and hence P is equal to 1%. So the area of reinforcement AST is 1963.5. So what we do, we provide 7 numbers of, recall the diameter of the main bar is 20, so 7 number of 25 diameter bars are provided. Now then we have to calculate the helical reinforcement, and for that we have the clause 39.4.1. So the volume of helical reinforcement divided by volume of core should be greater than this expression. Core diameter DC is actually 500, that is the diameter, and then the clear cover from either side is 2 times 40. So we have 420 millimeter. Then we can find out this expression on the right hand side. So that expression is 7.5 into 10 to the power minus 3. Now for 8 fibers, so ASH, that is the area of the helix, is 50 millimeter square. So volume of the helical reinforcement we can work out. It is, as you can see on your screen, 50 pi times 412 divided by SH. So volume of the core pi by 4 DC we have already obtained here. So this is DC. Then from this expression we can find out the value of SH, which is 62.3 millimeters. So what we do, we provide 8 phi bar as the spiral reinforcement with a pitch value SH of 50 millimeter. Right. So here is the cross section. As you can see, we have 7 main bars which are 25. Then we have clear cover 40 millimeter from this part to this part. Then this is, it should be 500. We have helical reinforcement of 8 phi with a pitch of 50 millimeters center to center. So that completes the design using PM interaction curve provided in SP16. So please go through the steps, and now you are familiar with how to design a column using biaxial bending. So you can try some other cross sections and then go through each and every steps. If you have any difficulty, do let us know through emails or in the interaction. So we'll clear your doubt. Thank you very much.